In this video, we will discuss how to analyze data through R Commander and R Script for ANOVA, and in particular for Oneway ANOVA, and also for contrast analysis. So I already have opened the R Commander window, and the data we're going to use is the Adler data set from the CAR package. So let's load that by going to Data, Data and Packages, Read Data Set from an attached package. Double-click CAR, double-click Adler, and click OK. So now that data set is loaded. First thing we're going to do is look at the descriptive statistics per group so we can get an idea of just what the data look like. So in R Commander, we can go to Statistics, Summaries, Numerical Summaries, and rating is the only numeric variable we have, so we will look at that. We're going to summarize by groups to get different output for different levels of the independent variable, and we're going to use the variable of instruction because it has 3 levels. Click OK. Click OK again. And so here we have the output in terms of mean, standard deviation, interquartile range, quartiles, and the sample size for the 3 levels of instruction, which are good, none, and scientific. We can also do this with our script. So let's open our R script in our studio. So first open our studio. And in this video, we're going to work back and forth between R Commander and R Studio. So I'll show you how to do something in R Commander, and then we'll do it in R Studio. We need to open our script file. So open file. Find the right folder. So the name of the script is Oneway ANOVA and Contrast Script for R. So to start, first we need to load the data in RStudio. So let's run the first command, and then let's attach that data set. And we're going to be using a new library, which is past ECS. So first we have to install that. So we need to go back to our basic R, packages, install packages, choose your mirror, and the package is PAST-ECS. So let's find that. Click. Once that's installed, we can go back to RStudio and load that package with the library statement. Gives us a warning, but that's okay. So that package has a function called stat.dsc, so statistics and descriptives, which allows us to get lots of basic descriptive statistics for different levels of the group. So by tells us we're going to be doing this for the outcome variable of rating. The grouping variable is going to be instruction. So let's run this. As you can see, we get lots of information down here in our output window. Make it bigger so we can see it all. So for all 3 levels of instruction, good, none, and scientific, we get NBR.VAL, which is the number of valid cases. This would be your sample size. And don't worry about these next 2. The minimum value, the maximum value, your range, sum of the values, the median score, the mean, standard error of the mean, CI mean 95. This is how you would get the 95% confidence interval, but this is the value that you would add and subtract from the mean in order to get that confidence interval. Variance, standard deviation, and the variation coefficient, which is the standard deviation divided by the mean. So we get a lot of information with this one command for each level of the independent variable. The next thing we want to do is to check for homogeneity of variance. So let's do it in R Commander first. So let's go to Statistics, Variances. For 3 groups, we need to use the Bartlett's test. So for our response variable, we only have the option of rating, factors. Again, we're going to choose instruction. Notice it gives us 2 pieces of information. So first it gives us the variance, which we know from this piece of the script. So the variance for each level. And then the outcome of the Bartlett's test, where our p-value is less than 0.05. So this means that we don't have homogeneity of variance. And if you look back at the variances, you can see that the variance for good, is about twice as much as the variance for scientific. So that's actually going to be a problem with just the basic ANOVA, but we'll still run the basic ANOVA, and then I'll show you how to run a corrected model for this lack of homogeneity of variance. If you want to test variance with script in our studio, we're going to do it in two pieces. So first we're going to get the variance for the outcome variable of rating for each level of instruction. We're using the tapply function to do this, and that just means the NARM equals true, means we're not worrying about missing data. So run that first. We get the first piece of the output that we got in our commander. And then the second piece runs the Bartlett test, so bartlett.test rating as a function of instruction, and the data set we're using is Adler. Run that, and we get the Bartlett's test. So now we're ready to compute our one-way ANOVA. So in our commander, we go to Statistics, Means, one-way ANOVA, choose our grouping variable, which is instruction. Let's click on pairwise comparisons of means so we can get a post hoc test, and then click OK. And as you can see, it just did a lot of stuff. It gave us a lot of information, and it even gave us a figure over in our regular R menu. So since this popped up, let's look at this first. These are the 95% confidence intervals for each pairing. So none compared to good, scientific compared to good, and scientific compared to none. And in all of these, the confidence interval includes 0. So this is telling us that our results are not going to be statistically significant, that none of the pairs differ from each other. But let's look at the ANOVA to verify that. So let's go to the top of the output. So if you find Bartlett's test, it's right after that. The output starts with the ANOVA source table. So we get the between set of values. And in this case, between is labeled with the factor that we're using for prediction. Residual is your error or within variance, and there's no total, but you can add things up to get the total. So you get the degrees of freedom first, then the sum of squares, the mean square, the f-value, and the p-value. So the p-value is telling us, consistent with what we got from the confidence intervals, that none of our groups are different. We also get some summary data, so you get mean and standard deviation and sample size just right within the ANOVA test, so that's pretty useful. We asked for the pairwise tests, so we're getting outcome for a 2-key test. And what this is telling us is it's comparing the difference between the groups to 0, the estimate, so these would be the values of the 2-key test, standard error, the t-value that is tested, and then the probability associated with that. So none of these pairs differ from each other. We also get the 95% confidence intervals of the difference. So these numbers, the lower and the upper limits, will map on to the values that we got in this figure. So none and good ranges from -7 to about 9.5. So you can see how those numbers match up. And this is telling us that each of the levels falls within the same group. Now let's do that with scripts. So back to our studio. So we need to specify the model and output the source table. So ANOVA model .1 is what we're creating. You can name this whatever you want. And then into that we are putting AOV, which is an ANOVA function, rating as a function of instruction using the Adler data set. So you run that, and it doesn't look like anything happens, but it's all in the background. So now we can output the summary of ANOVA model .1, and the only thing that it gives us is that source table. So it didn't give us all the other information that we got in our commander. It gave us just the source table. But if that's all you need, then that's great. So in this case, you would stop here. You would say none of the groups are different. But if this was statistically significant, then you would want to go on to conduct post hoc tests. So you could output the mean for each group with this command. It gives you the mean for each level. You can do the same thing for standard deviations for each level. And then let's say you want to do the Bonferroni. So one of the things that's nice about using script to do your one-way ANOVA is you have options in terms of which type of post hoc test you want to do. Whereas with our commander, the only thing you could do was the Tukey test. So we can use the function pairwise.t.test. Outcome variable is rating. The predictor variable is instruction. Paired equals false means that our data are not paired. We're not matching people up. They're independent, so that needs to be false. And p.adjust.method is the type of adjustment we're going to make to our p-value. So in this case, we're doing the Bonferroni adjustment. There are other options as well. Click Run, and this gives us a table that is all of the adjusted p-values for each combination. So we compare none and good, the p-value is 1. Scientific and none, the p-value is also 1, so these are definitely not different. And comparing scientific and good, the p-value is 0.66. So none of those are different. We can also do the Tukey test, so we need a new package, multcomp. If you haven't installed that yet, pause and go do that. Otherwise, just load it with the library command. And then we're going to create an object called Tukey. GLHT is the name of the function. ANOVA model.1, we have to take that ANOVA model that we created and put it into this function. That's where it pulls the information from. LINFCT, I'm not sure what that stands for, but that's how the function works, equals MCP. And then in parentheses, instruction, this is your predictor variable, equals Tukey, and this is where you tell it that you want to do a Tukey test. There are other options using this function, but if you want Tukey, that's what you need to put there. Notice it's in double quotes, and Tukey is capitalized. So we can run that. To output the results, we use summary Tukey. It gives us the same information that we saw in our commander, where the difference between the pairs is presumed to be equal to 0, and then the probability of those differences. We can also get confidence intervals with this command. So we get the estimate and the lower and upper limit for the difference between each pair, and then we can plot those confidence intervals using this command. Our plot's going to show up over here. If we want to see that better, we can just make the window better. This is the same figure that showed up in our basic R window when we've used the R commander. Next thing we're going to do is compute effect sizes. We're going to do this just in RStudio because there's nowhere to do it in R commander. So we can add to the output for the ANOVA model by adding this .lm. So summary.lm, where LM stands for linear model. And this will give us the eta squared effect size. So the part of this output that's important for figuring out eta squared is this multiple R squared 0.0172. So the groups are explaining about 2% of the variance, which is consistent with what we've been seeing before, that they're really not generating a difference in the ratings. If you want to calculate other effect sizes like omega squared, you would need to do that by hand using the formula that we learned in class, and you can use the basic summary ANOVA Model 1 output to pull the information you need for that formula. We can also find effect sizes for pairs. So the library we need to do this is compute.es. So more than likely you're going to have to go install that package. Once you've installed it, then you can load it in RStudio. Just warns us it was built under an earlier version, but that's fine. MES is the function, and what you input here is the mean of the first group, the mean of the second group, standard deviation of the first group, standard deviation of the second group, and then your two sample sizes. So this is going to compare good to scientific. So you have to get these numbers from the output that you created earlier. And when you run this, you get a lot of information. So let's go up to the top. So you get effect size D, you get the estimate of the effect size, negative 0.31, but also the confidence interval around that. And then you get a bunch of other stuff that I wouldn't worry about. You just really need to focus on this top line, and this would be the effect size that you would report, this negative 0.31. There are other effect sizes here too, so there's G, another type of effect. You can get the correlation, the R effect size, again, the estimate and a confidence interval. You can get effect size in terms of Z, and then there's also an odds ratio and a log odds ratio. So there's lots of things you get with this little tiny MES function. That's kind of cool. We can also use figures to help us check the assumptions of ANOVA. So we've done this once before, but we can change our layout to have a 2x2 layout. So run that. Now we can plot ANOVA model 1. So you have to actually run the ANOVA before you can check for the assumptions, which seems a little backward, but that's it. Just uses that information from the ANOVA itself. So these are plots we've looked at before. So fitted versus residuals. Looks pretty good. There's a couple of outliers, 7.1, 86. We've looked at this before. Fitted values by the square root of the standardized residuals. So these tell you about the same thing. There's that normal QQ plot again where we have outliers on the high end and the low end. And then the residuals versus average where again we have some outliers. So here, finally, we get to the ANOVA that we should be running for these data because we violated the assumption of homogeneity and variance, and we're going to use the Welch correction to deal with this. So the function is oneway.test, and in parentheses, rating as a function of instruction. Click Run. So it tells you one-way analysis of means, not assuming equal variances, which is what we need. The F value is very small. Numerator degrees of freedom are 2. Denominator degrees of freedom, 60.799. That's one of the places you'll see the adjustment having an impact. And the p-value is 0.3748. So even with the adjustment, we're still not finding statistical significance. And oftentimes you'll find that even when you do the adjustment, you still get the same decision as you would without the adjustment. But sometimes it makes a difference, and this is just the correct way to do it. Okay, the last thing we're going to do is the contrast analysis. So it's called plan contrast because we planned these in advance. So first we need to do is create new objects that contain the contrast weight. So we're going to actually do 2 contrast weights, 2 different ones, contrast weights of 0, -1, and 1, and contrast rates of -1, -1, and 2. And it's very important to be sure that the numbers are in the same order as the levels of the predictor. So if your predictor is numeric, you would want to make sure that your contrast weights match up number-wise with those values. If it's a factor, then they should be in alphabetical order. So contrast 1, let's create that. And then contrast 2. And now we're going to connect the contrast weights to the levels of the predictor. And we do this by using contrasts, in parentheses, the name of the data set and the name of the predictor variable. cbind combines these 2 objects that we created, contrast 1 and contrast 2. So let's run that. And then if we want to see what this looks like to make sure it worked, we can run this statement, which is just looking at the instruction variable and the Adler data set. So the first thing that it gives us is the value of that variable for each participant. And then it shows how that matches up with the contrast weight. So the first contrast, good is 0, none is -1, and scientific is +1. And then in the second contrast, both good and none have weights of -1, and scientific has a weight of 2. And then you can run ANOVA with this new information. So now the Adler data set has this additional information of these contrast weights. So when you run the ANOVA, the AOV, with that data set, even though it's the same as before, you're now actually going to look at how those contrast weights are impacting things. So this ANOVA.contrast, you can name the object whatever you want. I just thought this would be a good way to remember that this was the contrast analysis. And then for the summary, you want to use that .lm again to get the additional information that you need beyond just the source table. And make sure that the object you put here is named consistently with the object you created right above there. Okay, so here is the output. We get residuals, coefficients, And this is where the contrasts are. So here's how well the data fit contrast 1, not well at all. And contrast 2, again, it doesn't really fit that very well at all. It's probably not going to fit any contrast where you're predicting a difference since there are no differences. Don't worry about this part down here. Really the piece you want to focus on is these two contrasts. Okay, so that is how to do one-way ANOVA and contrast analysis in R Commander and with R script.